solve 2, you should be able to do 3, 4, and 5. Because sometimes they're not given to you, okay? You may be given both sides are open, and then you have basically a wave that has to go clockwise looking down. So I will be clockwise. Right? Or let's say if they meet here. If they meet again, they're going to combine to have the same current, okay? So that was Kirchhoff's rules, right? Okay, and then combine that with my concept, you guys should be able to master all of the circuit problems, remember? And then we did the direct current circuits where the current never changes direction, right? That's direct current, that's what it means. And I show you guys how to resolve all of the junctions and all of the series, right? The parallel. And then I show you RC circuits, remember? Where I had the capacitor in there. So when you have the switch just closed, just think of the capacitor as the conductor, right? Conducting wire. So just connect that and treat the system separately, like as a wire, okay? But when you have the switch closed for a long time, the capacitor becomes an infinite resistor. Okay? Infinite resistor such that you have no current going through that section of the wire. No current through wire. So that means that if there's any resistance that is in series with the capacitor, that means that there's going to be no current. Okay? So you can consider that resistance obsolete. So that resistor will have no current. So that whole wire is like gone, basically. Okay, so if I have this, for example, and then a capacitor, right? After the switch has been, closed for a long time, this whole wire will be gone pretty much. So this capacitor destroys any current going through this. So if I have a junction here with a resistor here, basically all of the current will go through that. It won't go through there anymore. Okay? All right. So those are the two conditions you need to remember. And then after I did this, we ended that electricity section, right? And then I talked to you about magnetism, and I showed you about the magnetic force, right? Magnetic force only acted on moving charges, right? And the magnitude was equal to QVB, right? Absolute value of Q, VB sine theta, where theta is the angle between V and B, right? And then I also talked to you about how to figure out the magnetic force on a current, right? Carrying wire. And that was just equal to IBL sine theta, right? Okay? And I also talked to you about the right-hand rule, right? For each of these. For example, for moving charges, the motion, right? You put your thumb here, the motion, and then you put your other fingers in the direction of the magnetic field, right? And then you curl it so you can figure out where the force is going to be, okay? So, and then for this one, you use this where you can use like your thumb, right? Oops. Your thumb will be in the direction of, let's say, the eye, and then the way that your finger gets curled, right, will be the magnetic field, sorry. And then for the magnetic field, then you can go and use the magnetic force, right? Okay? Because the magnetic field is along the direction of the magnetic force. Okay, so after I show you that, then I talked to you about how to determine the magnets, right? The idea of going through this magnetic field, and then you have the north and south poles, right? For example, I have a loop, right? And then I carry this through, right? North and south. What happens to the current induced in the loop? Remember, this is Lenz's law. before we did that, we had to figure out that the I, right? If I going out of the page, which way is the magnetic field going to go? Right, it's going to go like that, right? Just using the right-hand rule. Thumb here, roll, right? So it's B. So when this happened, and then if you have like this, so it's going to be like that, right? Okay? So that's how you do it for B here. So then I show you that, okay, when you have Lenz's law, it's like the opposite of this. So instead of having a current producing a magnetic field, you're going to have a magnetic field producing a current. So these are opposites, okay? So here you see Lenz's law says, okay, well, what are my magnetic field lines? Okay, they're going like that. So if I push this magnet down, right, I'm going to get an increase in magnetic flux upwards, right? But this increase in magnetic flux upwards will be counteracted by the current that's produced, because it will go to increase the magnetic flux downwards. In order to do that, it has to produce the magnetic field going down. In order to do that, which way does it have to go? It has to go this way, right? I. Okay? So that's how you do Lenz's law. Remember? Lenz's law is like this. So when there's an increase in the magnetic flux upwards, let's say, right, the system will produce a current that will try to counteract that increase upwards by producing a magnetic field that would increase the magnetic flux downwards. Okay? So that's how it works right there. But just look at this and simply know that, okay, if these lines are going up, right, increasing, right, up, they'll try to go, so the I will try to produce a B that will go down. So this going down, that's what determines the direction of the I, okay? All right, and then there were some equations that dealt with the magnetic flux, right? You had to remember that. For example, for the current producing the magnetic field, B is equal to what? Mu naught I times 2 pi over R, and you do know that FB on the wire, IBL sine theta, and you know that Faraday, he said that magnetic flux is B times A cosine theta, right? And that the epsilon is equal to the negative change in the magnetic flux over delta T, right? So you plug it all in and you get this is equal to negative B LV, okay? So that's the potential difference created by moving the conducting wire through the magnetic field, okay, at a certain velocity. Okay, so for homework, you guys, I would like you guys to make for me a concept chart, okay, where you do electricity and magnetism. See all the things I show you just right now? I want you guys to try to find a way to connect electricity and magnetism together. Remember the flow chart? Like you go with Coulomb's law, right? Then you can connect it to electric field, so on, okay? And how is electric field connected to the potential, right? Electrical potential energy and so on, right? Okay, do that. And then give me the equations along with it, okay? So that's what you should do for homework for me. Next time, I will briefly cover optics, and then we'll go into general problem solving, okay? Where I will, give you guys problems from, any section in the classical mechanics or in the electricity and magnetism. I'll give you guys problems, to review, okay? And we'll do them together. Okay, so it's all going to be devoted to problem solving. And like I said, I've already dealt, with the concepts, but you guys were fortunate because I was actually interspersing the concepts with problems, because in physics, it's difficult to just teach you guys concepts and no problems, right? So I had to include problems along the way. So you guys have already had a dosage of all of the problems I gave you. However, we will be focusing more on the problem-solving tactics and skills in the next couple of lecture videos, okay? So get ready for that, and we'll go over some free response questions, okay, from the test, practice test. And then I'll give you guys some hints as to how to approach a physics problem, okay? And so please do this for homework for me. And I think that's about it. So I'll see you guys next time for the optics and for problem solving, okay? Thank you very much.